Right.
Did the recording actually start?
I think so, but I didn't hear anything, but it could just be because,
So conceivably.
yeah. So, yeah, I just wanted to talk about, well, I guess Steve left, but I wanted to talk about what I did over the summer for
Yeah, speak up a little bit.
ordinal graph
I can't even
algebras.
hear you from here.
Okay. So in particular, I found a class of ordinal graphs, which are naturally Cuntz-Pimsner algebras. I wanted to describe some of the cooler details of the proof and leave out some of the less interesting details of the proof. But it's kind of a long talk, so it's okay if I don't get through everything. Recall that an ordinal graph is a category, which I'm calling lambda, and a functor, which determines how paths in the category factor. So for every path E in our ordinal graph and every n less than the length of E, that path E factors uniquely as F and G, where the length of F, the factor on the left, is n. And n can be an ordinal. If n is finite, or if the range of D is finite, all finite ordinals, then it's a directed graph, but in general, n can be an ordinal. And source of E and range of E are denoted by the functions S and R. Now I have new notation compared to last time's talks on ordinal graphs. The factor on the left I'll call E of n. So if you factor off from the end of the path, a path of length n, that's E of n. And the right-hand factor I'll call E of n inverse E, so that you always have E of n inverse E is equal to E. Now, there are a certain collection of paths that I will define here. So superscript alpha is all paths of length alpha. Subscript alpha is all paths of length less than omega to the alpha. And superscript omega star is all paths which are which have a length which is a power of omega. So the C star algebras for the ordinal graphs are universal for generators, for paths which are either vertices or paths of length some power of omega. They satisfy these four relations. And since each lambda sub alpha is an ordinal graph, then you actually have a lot of different C star algebras all associated to a single ordinal graph. So the lambda sub alphas, remember, they're the paths of length less than omega to the alpha, and you compose two such paths and you still get a path length less than omega to the alpha, because the sum of two ordinals, which are less than omega to the alpha, is still less than omega to the alpha. So we can form the C star algebras for all of these associated subcategories, lambda sub alpha. And you look at the generators and relations, and just as in the case for a directed graph, you have automorphisms for each alpha on the C star algebra for lambda sub alpha plus 1. These automorphisms, they twist a path of length omega to the alpha by z, and they fix any path of length less than omega to the alpha. Every ordinal which is less than omega to the alpha plus 1 is some finite sum of omega to the alphas plus some ordinal smaller than omega to the alpha. So these two relations determine the automorphism. The universal property for these C star algebras are universal for these relations, and the universal property induces homomorphisms, which I'm calling rho alpha beta, from the C star algebra for lambda alpha to the C star algebra for lambda beta, simply because when you go from lambda alpha to lambda beta, you're strictly adding generators, and you're adding no relations involving previous generators. So For sufficiently large beta, because maybe I didn't write it in my definition, but lambda is required to be a set so we can even form a C-star algebra. And ordinals are large enough so that for sufficiently large beta, lambda beta is equal to lambda. So in particular, the C-star algebras are equal. And we can speak of the homomorphisms, just rho alpha, which are the homomorphisms for the C-star algebra for lambda alpha, just into the C-star algebra for the ordinal graph. Then one of my main questions is, when is rho alpha actually injective? So it doesn't always happen. So here's a somewhat enlightening example, same time pretty simple. You can consider a category generated by two objects, V and W, two morphisms, E and F, and a morphism G, which goes from B to V and satisfies the relation EFG is equal to G. So you consider the most general category satisfying these relations. Then row 1 maps the directed graph. So that's the directed graph you get by considering just the paths length 1, E and F, and the vertices V and W, into the C-star subalgebra generated by TV, TE, and TF. And then in this category, G is the unique path of length W whose range is V. So I'm not going to, just because I'm already strapped for time, I'm not defining alpha regular vertices, but that is essentially what it means. For that essentially tells you that G is the range of G, which is V, is one regular. And then relation 4 tells you that TG star is equal to TV. So the range projection for TG, which is a partial isometry, is TV. Then you can see what this implies in the C-star algebra. So in particular, you have EFG is equal to G. So you can take the partial isometry for EF, and you can multiply on the right by TV, and then replace TV by TG star, and then TG absorbs the EF. So what you end up with is that TEF is equal to TV. And this is in the image of row 1, but row 1 is the directed graph, which is just a single cycle of length 2, and the C-star algebra is 2 by 2 matrices over continuous functions on the circle. And you can verify that TEF is not equal to TV in that C-star algebra. So we have, in this case, the kernel of row 1 is not equal to 0. You don't need to know too much about the C-star algebra to verify that the kernel is not empty. So you can use just the gauge action. What you do is you take this equality, TEF is equal to TV, and you apply the gauge action to both sides. On the left, we have a factor of Z squared, and the gauge action fixes TV. So you end up with Z squared TEF is equal to TV for all Z on the circle. And that's a contradiction. You just select Z is equal to 1, Z equal to I, and you get that TV has to equal 0. And I'll show you a representation of these algebras which tells you that the vertices are never 0. So yeah, the kernel of row 1 is, in this example, not 0. But as I'll show you, the real reason why row 1 is not injective is because we have a path of length omega, which factors through a cycle. So in other words, in this case, EFG is equal to G, and EF is a cycle for which the range is 1 regular. It should be 1 instead of 0. Okay, so, but this all relates to correspondences. So now I have to tell you what these C-star correspondences are. First, you set X alpha circle. This is going to be the thing we complete to get the correspondence. it's the finitely supported functions on paths of length omega to the alpha into the C-star algebra for lambda alpha. But you only take functions which satisfy this relation involving the source vertex projection. Then you define the left and right actions. The left action, you have to use generators and relations to show that the left action is well defined. But here's what it does, what the left action for generators is. Then you define the inner product by just taking FE star GE and summing over paths. And in the end, after completing, using the norm you get from the inner product, you get a C-star correspondence, which I'm calling X alpha. And if you set alpha is equal to 0, and the correspondence you get is isomorphic to the usual C-star correspondence for a directed graph, you just have to make some identifications having to do with this condition here. So I've constructed these C-star correspondences so that they have a representation. How do you get it? Well, first note that X alpha is spanned by these delta E functions. So delta E is valued at the source projection for the path E and 0 everywhere else. And then X alpha is the closed span when you take the span over the coefficients of these delta E's. So you define this psi alpha by linearly extending, it's uniquely defined by psi alpha maps delta E to T sub E in the C-star algebra for alpha plus 1. And then it turns out psi alpha and rho alpha alpha plus 1 form a Toeplitz representation of the C-star correspondence X alpha. And in our previous example, we saw that this representation isn't always injective, because injective would mean that rho alpha alpha plus 1 is injective. So we can't hope in general that the Cuntz-Pimsner algebra for X alpha is isomorphic to the algebra for lambda alpha plus 1. But as you'll see, it happens for lots of ordinal graphs. In order to tell you which ordinal graphs it happens for, I have to make another definition. So I'll call a path alpha cancellative if for every P and Q length at less than omega to the alpha plus 1, you have that this equality PQ inverse E is equal to Q inverse E implies P is actually has length less than omega to the alpha. And I didn't really know what else to call it, but
Maybe you could assign homework to.
yeah, that's your homework, yeah. I'll call for now lambda to be normal if for every path of length omega to the alpha whose range is alpha regular, this path is beta cancellative for all beta less than alpha. And actually, you know, being an alpha regular vertex is so strong that this is equivalent to just having that for a path E length omega to the alpha whose range is alpha regular, FE is equal to E implies F is a vertex or length of F is 0. So in a way, you're canceling the E's on the right. You have to be able to cancel the E's on the right when you have these paths. And then at some point, I'll just give up trying to do everything in full generality, and I'll just use alpha is equal to 0. So I'll call that just cancellative when alpha is equal to 0. And for alpha is equal to 0, we have finite length paths for P and Q. Okay, so the main theorem is that if you have a normal ordinal graph, then for all alpha, these Toeplitz representations, which I've only shown you are Toeplitz representations, are actually covariant representations of the C-star correspondence. And in particular, the rho alpha to alpha plus 1s are injective, and the C-star algebras which are the Cuntz-Pimsner algebra and the algebra for alpha plus 1, are isomorphic. I want to show you how the proof works, but it'll rely on these two lemmas, and I'll just see how far I can get in actually showing you how the proof, some of the bits of the proofs of those two lemmas actually work. But for now, let's assume that we have an arbitrary alpha and that, say, the result holds for all beta less than alpha, and that we have the following lemmas. So we can prove separately that rho alpha is injective whenever lambda is normal, and that the Katsura ideal for the correspondence is generated by the alpha regular vertex projections. This Katsura ideal, remember, these are the things where the left action acts by compact operators, and they're in the annihilator of the kernel of the left action. Since rho alpha is a composition with rho alpha to alpha plus 1, rho alpha to alpha plus 1 is injective since rho alpha is injective. And the strategy is to show that you have a covariant representation and then use gauge invariant uniqueness theorem. So here's how you show covariance. You define this ideal I. This is an ideal of the Katsura ideal, and it's the ideal such that the covariance relation holds. So this map here, it takes compact operators into the Cuntz-Pimsner algebra, and in order for the representation to be covariant, we need this to hold for all members of the Katsura ideal. So I'm just taking the ideal of things in the Katsura ideal which satisfy that relation. You need to know a few things about this homomorphism to actually prove it's an ideal, but it's an ideal. And since J alpha is the smallest ideal containing the alpha regular vertex projections, it actually suffices then to show that each alpha regular vertex projection belongs to this ideal I. And this is directly from relation 4. So really, you apply this map to this compact operator, you get sum of SC star, where E is a path of length omega the alpha ending in V. And here I'm using SE to be a generator for lambda alpha plus 1 C star algebra. And this E by relation 4 is equal to rho alpha alpha plus 1 of TV. So proving that each TV is an I is direct, and then it follows from the lemma that J alpha is generated by these alpha regular vertices that representation is covariant. So for gauge invariant uniqueness theorem, you need a gauge action on the image of the representation, which is covariant with respect to the gauge action on the Cuntz-Pimsner algebra. So where does that gauge action come from? Well, it's exactly the gamma alphas I defined earlier. You can do these calculations, check separately what happens for delta E's and what happens for, say, A, where A is in the C star algebra for lambda alpha. And you get that the gamma alpha Z is covariant with respect to this gauge action on the Cuntz-Pimsner algebra. Then by lemma, we also know rho alpha alpha plus 1 is injective. So gauge invariant uniqueness theorem tells us that C star algebras are isomorphic, and that this representation we have psi alpha rho alpha plus 1, rho alpha alpha plus 1 is universal for covariant representations. Okay, so that's how we get the isomorphism. But now what remains is these two lemmas, and these two lemmas are where the majority of the hard work is. first thing I'll show you is how do you prove that row alpha is injective when lambda is normal? And my strategy I use to prove this is to find some representation pi of the entire ordinal graph algebra, and then use that, and then prove that pi composed row alpha is injective using the hypothesis that the theorem is true for all smaller ordinals, and then it follows that row alpha itself is injective. There are certain representations for graph algebras you can construct, which are always injective. These involve boundary paths. So what is a boundary path? It's just a sequence of edges that would form a path. So source of EK is range of EK plus 1, but it can possibly be infinite. If it's finite, then the source vertex for the composition of the entire path, all the paths, has to not be a regular vertex for the directed graph. Anyways, you take all such collections of possibly finite sequences of edges, and you call that partially boundary paths for the directed graph. Then you can define a representation of the graph C-star algebra into bounded operators on L2 of boundary paths cross Z. And the job of the Z is to keep track of information that'll let us make a gauge action. So a generator acts on a vector psi fn just by composing with E and then adding the length of E to n. This is a representation of the graph C-star algebra. And if you define unitaries on this Hilbert space by saying that a unitary acts on psi fn by multiplying it by z to the n, then you get that the gauge action is implemented by conjugating with these unitaries. So you can do this calculation, and it shows you that conjugating by first applying pi and conjugating by uz afterwards is the same as first applying the gauge action and then applying pi. For every vertex, you can find a boundary path with that vertex as a range of that boundary path. And so this representation, in this representation, the vertices are not mapped to 0. And then gauge invariant uniqueness theorem implies pi is injective. So this works for an arbitrary directed graph. Now my plan is to do something sort of like this, but for an ordinal graph. But we have to define boundary paths for an ordinal graph. And it's a messy definition, at least the way I'm defining it. There's probably a cleaner way. However, you can think of them the same way. You're just looking at first maybe just finite length paths in your ordinal graph, but you're looking at how you can continue to extend them backwards. And the rule is, the rule here is here, and informally it says, if you stop at a vertex, which is say alpha regular for some alpha, then you have to extend by at least a path of length omega to the alpha. So if you continue along your boundary path, find some vertex in the middle, which is alpha regular, then the rest of the boundary path has to at least be a path of length omega to the alpha, or even larger. So I actually don't think I refer to it later in the slides, but this L function is telling you how long your boundary path is, but it's distinct from this functor D, which tells you the length of paths in your actual category. This L tells you you've taken a collection of paths which are all have length less than beta. or less than alpha. And the key feature for boundary paths is that if you compose with a path on the end, you still have a boundary path. And if the range of the boundary path is alpha regular, then L of f has to be greater than omega to the alpha. So that's this defining property for boundary paths. You can also factor off paths from a boundary path and you still get a boundary path. From now on, I'll be specializing to alpha is equal to 1. And I need an auxiliary function. It'll take boundary paths to integers, and it has to satisfy these 3 rules. The most important one is this 3rd rule. If you have a cancellative boundary path and you have some finite length path, then this V of the composition, or sorry, here I'm specifying a path of length 1. So then V of the composition is 1 plus V of f. In order to do this, you can't do it for all boundary paths because you might have some that loop through themselves. So there's no consistent way of assigning these integers, but you can do it exactly for the cancellative boundary paths. And the other 2 conditions are just needed to make the following representation I'll show you actually give you a representation. So the representation for the entire ordinal graph algebra on B of L2 of boundary paths cross Z is defined by this. So you compose with the generator, but you change the integer. How do you change the integer? Depends on whether the composition is a boundary path of length less than omega or length greater than omega. You can check very tediously that the operators pi of TE actually do satisfy the 4 relations for the ordinal graph C-star algebra. So this is a representation of the entire ordinal graph C-star algebra. Now consider this closed subspace generated by looking at only the paths with the boundary paths which are cancellative. Then if you cancellative paths are closed under taking compositions with finite length paths and factoring by finite length paths. So what that means is K is an invariant subspace for pi composed with row 1. And this invariant subspace is how you get the gauge action, some action which is equivariant with respect to the gauge action. In particular, same trick. You take unitaries on K now, defined by raising to the Z to the power of n and multiplying. And this second bullet point is the key part where I actually use that lambda is normal. Though I won't show you the proof of this, I can kind of give you an idea of how the proof goes. But the thing you actually need is that if lambda is normal, then for every vertex, there's a boundary path, which is, I think there's a mistake here. It's either cancellative or has length greater than omega. How do you do this? Well, you either have a, so you can take your vertex and start following edges backwards. You either can hit a cycle or you can't hit a cycle. If you can't hit a cycle, then you can just choose an arbitrary boundary path. If you can hit a cycle, then you go to that cycle and you keep going around that cycle over and over again. And since the ordinal graph is normal, none of these vertices can be one regular in that cycle. So they are boundary paths according to the definition I gave you. So that's how you actually prove the second point. And since these unitaries implement the gauge action, so if you conjugating by these unitaries is equivariant with respect to the gauge action on the this is the gauge action on the C-star algebra for the directed graph lambda 1. So since you can implement the gauge action and these vertices are all mapped to something, to an operator which is non-zero, then gauge invariant uniqueness implies that pi composed with row 1 is injective on this invariant subspace K. In particular, row 1 is injective. Okay, so the other lemma is that this Katsura ideal J1 for the correspondence X1 is generated by the one regular vertices. And here I take two steps. First, I prove that it's gauge invariant, and then I apply the classification of gauge invariant ideals of Cuntz-Pimsner algebras. So you can see that the vertices are invariant under all the gauge actions. Here we just care about gamma 0. So it actually suffices to show not just you don't have to show that J1 is the smallest ideal containing those vertex projections. You only have to show it's the smallest gauge invariant ideal containing those vertex projections. So I'll also use unitaries to prove that J1 is gauge invariant. The way you do it is you define these unitaries, but now these are unitaries for the correspondence X1, but they're defined by UZ acts on delta F by multiplying by Z to the power of V of F. I'm using this V function from before in the other lemma. If you look at a path length omega, which is cancellative, then some finite length path whose range is F, this should be an edge, not a finite length path. Anyways, you compute that the composition V1 with the gauge action does this to the vector delta F. And then you can rewrite that using as conjugation by UZ. This is as long as the path is cancellative, because we only know that V satisfies the required property for cancellative paths. Then you have, for cancellative paths, the composition of V1 with the gauge action agrees with conjugating by UZ after applying V1. So if we can prove that for some member of the Katsura ideal, V1 composed with the gauge action applied to A sends delta F to 0 if F is cancellative, then it actually follows that V1 composed with the gauge action is equal to conjugating by Z after applying V1 for elements of the Katsura ideal. And if A is in the Katsura ideal, then the left action by A is compact. So conjugating by unitaries doesn't change whether it's compact. So that means that the gauge action applied to A still acts by compacts. So then if we also prove that the gauge action applied to A is in the annihilator of the kernel, we'll have gauge invariance. But for this, you just use a trick. You unwind the gauge. So we choose an arbitrary B in the kernel of phi1, and we unwind the gauge action. So here, this equality is what we're using. Then phi1 of this is because of this equality and the fact that A times the gauge action by Z bar applied to B is still in the Katsura ideal. This is equal to conjugating by UZ after applying phi1 to this element. And since B is in the kernel, it's also equal to 0. and conjugating by uz doesn't change whether you're equal to 0. So phi1 of A times z bar acting on B is equal to 0. And then the left action is injective on the Katsura ideal. So A times z bar acting by B is equal to 0. And then you can rewind the gauge action. You get that z acting by A times B is equal to 0. So indeed, the gauge action applied to A still lands in the annihilator of the kernel for U1, and you have that J1 is gauge invariant. But all of this relies on knowing that V1 composed with the gauge action acting on a cancellative path, it sends a cancellative delta F to 0. So we reduce the problem to that. So how do you prove that? So that's all we need to prove now. You can go back to the definition of cancellative. And you can see that if F is not cancellative, you have some finite length paths for which this equality happens, and the length of P is positive. The main thing to focus on is this power of TP. This equality holds for all n. Since you can unwind the gauge action and absorb the Q into the A, it actually suffices to prove that whenever P is a positive length path, A is a member of the Katsura ideal, then this sequence approaches 0. So this is stronger than just sending the vector equal to 0, but it's actually true. How do you prove this? Well, you can fuss around with the compact operators and the correspondence and prove more generally that if you have any A who acts by compacts on the left and some positive length path, then phi1 of A times powers of P actually has a norm convergent subsequence. So I did this by just some direct argument once I knew what the operators which acted on the left and which were compact looked like. So I won't describe that. But then you can see that if, in particular, if you have a member of the Katsura ideal, since phi1 is injective on the Katsura ideal, it implies that A times some increasing sequence of powers of TP converges. We don't know what it converges to, but that's what we'll see. It converges to 0. How do you prove it converges to 0? Well, I want to do this in a way that only uses information we have for ordinal graphs. So I use the gauge action here. The gauge action is continuous, and so you can average the gauge action over smaller and smaller epsilon. You take e to the it acting on B, and you average that for smaller and smaller bounds on T. And since the gauge action is continuous, you get back B when you take the limit. But actually, these integrals are all equal to 0. So you can compute, pull out the limit by continuity. You get these powers, e to the ink, length of P, which is positive, T. Then you use dominated convergence theorem to pull out the limit from the integral, and then you can factor out the TPs in the integral. And it turns out that the limit of this integral here is 0. How do you see that? Well, you could, for instance, apply a state, because this is an element of a C-star algebra and states are faithful. So you apply a state, and then by linearity, you move it inside the integral, and you'll see that in the end, you're computing the value of the Fourier transform with respect to T at increasing inputs, nk length of p. And Riemann-Lebesgue lemma tells you that you take an L1 function, you take the Fourier transform, you get something which vanishes at infinity. So the limit of these integrals is 0. And since the norm of Tp n to the k is 1, it's a partial isometry, the entire limit is 0. Then you can take the gauge action applied to B, so B is 0. You use the definition of B, you get that this sequence is 0. But the z's have norm 1, so that implies that the sequence without the z's is 0. So that's all the steps for gauge invariance. Now we know J1 is gauge invariant. So then my plan was to use the classification of gauge invariant ideals for Cuntz-Pimsner algebras. Here is sort of a simplified version of this classification of gauge invariant ideals. If you have a gauge invariant ideal of Cuntz-Pimsner algebra and say psi pi as the universal covariant representation, and it should be, yeah, for a correspondence X over A, then the gauge invariant ideal is completely determined by these two intersections. So you have to take the intersection of the ideal with the coefficients, and then you have to take the intersection of the ideal after adding all the compacts with the coefficients. And very
Am I wrong to say there's an obvious relation between those two ideas?
sorry.
Am I wrong to say that one of them is contained in the other, obviously?
No. That you do have this containment, but it's still classified by both intersections.
Oh, I see. You're not sure that there's.
No. I'd like you to note that it's kind of a mess here, but really what I'm doing is 0 is a member of every ideal. So this ideal here, it always contains the intersection of the compacts with the coefficients, which is always the image of the Katsura ideal for that correspondence. And that's going to make our lives easier. Because this is one of the lemmas that I'm not going to show you how to prove, but it's more just direct fussing with compact operators. You can prove that for our correspondences, this intersection, the bigger one, is contained, that should be, I really messed this up, didn't I? So this alpha should be a 0, this alpha should be a 0. This should be the image of J0. This is the Katsura ideal for the previous correspondence. So then, by this containment and by what was supposed to be this containment, you actually have that this intersection is the image of J0. But for every gauge invariant ideal containing J1 intersect coefficients, you have to have that gauge invariant ideal contains the image of J0. So in fact, J1 is the smallest gauge invariant ideal of the Cuntz-Pimsner algebra containing, I also messed this up, didn't I? This should be lambda 1, because we're looking at an ideal of our coefficients.
It's okay, the slides have not been posted yet.
Yeah, this was a bit last minute, so. Anyways, J1 is the smallest gauge invariant ideal containing the image of the vertices. So all you have to do to finish off the proof is to show that a vertex projection is in the Katsura ideal J1, if and only if it's one regular. oh, this is the last slide because I figured I'd just explain away the rest, but
You just said this finishes the proof.
does, yeah. I wish I would have added, it just follows from relation 4 again in the C structure. So yeah, this is the long, oh yeah, also. I showed you, I specialized to alpha is equal to 0. But really, all of these proofs go through for every single alpha. It just gets more, you just have to bookkeep. And there's a part of the argument that changes, but it's the same ideas throughout. Yeah.
This, can you go back to the theorem, the main theorem? So perhaps this is a naive question because I understood about 3% of this, but does this characterize normal ordinal graphs? Like,
Yes, yes, good. Thank you for asking that because, yeah, normal ordinal graphs. So I showed you the example where you have a path of length omega factoring through a cycle, a finite length, whose range is 1 regular. But in general, if you have a path of length omega to the alpha, which factors through a cycle in lambda alpha, whose range is alpha regular, then you can show that row alpha is not injective. So normal ordinal graphs are precisely the ordinal graphs for which all these rows are injective. I don't know what happens when, like, how do you determine when one is injective and another isn't? Like, if you have that simultaneously, I don't know, but yeah, and also in our example, I showed you that the representation isn't even, it can't be a universal universal covariant representation. And also that holds, so if you don't have a normal ordinal graph, then there's always going to be some alpha where this fails.
I have a question which is, I think, pretty much unrelated to your talk, but it's related to the C-star algebras. So you look at the higher and higher powers of omega, and to get from each one to each algebra to the next one, you're constructing a correspondence and you use Cuntz-Pimsner algebra.
And to go to a limit ordinal, you take an inductive limit.
This is very similar to what I've been doing in this you notice this already.
Yeah.
This thing with the K-graphs and they going up and up. I wonder if there's anything going on there.
It's interesting because K-graphs are kind of like orthogonal to ordinal graphs. Instead of making the paths longer, you add more room for the paths. It seems like a kind of opposite generalization in a way. So maybe.
Okay, so this is a relief, so I don't have to mention your paper in our paper.
No, but I would like it if you did.
I like one.
Sure.
Did you get through what you wanted to get through? You don't need any more times.
I didn't even think I'd get through all the slides, but I guess I did. So.
The only remaining question is, did anything actually get recorded here?
Oh yeah.
Guess I'll get if so, I'll get an email notification.
Yep. Let's see. I can stop recording.
Okay, so